Hi everyone, welcome to our presentation for ME 435 in the modulus of autonomous vehicles. Today, Matthew Gani, Ahmed Altaneji, and me, Isaac Arbelaz, will be talking about some of the parts that we actually work on during the lab. So first, we want to show you the contents. So we'll go through a little introduction of what the task was, what was our main goal. Then we're going to see how we actually started to learn more about how to achieve those goals in the learnings of the labs. Then we're going to go through the flowchart of how we designed what we were actually going to achieve during our final task. Then the final task showcase of how we actually end up achieving this, our end result, and finally the conclusion. So, as mentioned for the introduction, we were given the task to program a robot to travel from location A to location B. This specific robot was the NVIDIA JetBot, which is a differential drive robot powered by the Jetson Nano AI computer. In order to achieve this travel location, there are a couple constraints and couple obstacles that slowly but surely, through the different lab progression that we're learning, we're able to tackle, such as how to make it autonomously, how to find the shortest distance, how to find make the robot to actually follow a road, as well as follow different traffic signs. In the end, our main goal was pretty much to combine all these different complex computer vision as well as hardware calibration to finally make a fully integrated network global navigation system for the robot. So then, simple tasks such as going from location A to location B is able to have all these different complexities integrated into it. In Lab 1, we were focused on the hardware calibration and kinematics. To do this, we were introduced to Python and basic robot control by first getting familiar with some of the commands and functions that we'll be using for the rest of our project. Once we established this physical foundation in connection between the hardware and the software, a critical challenge we faced was that the JetBot lacks internal wheel encoders. To solve this, we performed manual odometry calibration by timing the robot as it traveled over set distances on a straight driveway. The issue was that sometimes, even though we had the same input for both motor values, so both the left and right, we'll be seeing some drift from the robot. So in order to fix this, we actually develop a calibration table and apply the specific values for the bias, in which we'll be ranging between 0.028 to maybe 0.019 to ensure that the robot maintain a perfectly straight heading. After setting this calibrated movement, we actually use inverse kinematics to have a little bit more complex movements. This complex movement was actually to find a way in which the robot will be going to an intersection and then turning whether to right or left. So we calculated some rotational parameters to perform this specific 90 degrees turn on the intersection. And in some way, we both combine the translation and rotation in this movement. So therefore, we were able to find this accurate hardware calibration to actually perform the movement and the kinematics for the robot. In lab 2, we moved from this basic control into more towards the perception and feedback control. To allow the JetBot to follow a path, we use the onboard camera and implemented HSV color masking to isolate the yellow and white lines on the road. This would allow us to isolate these specific road paths in which we'll be using values, so then the robot is actually getting just the image that we want. In this case, our values were for the lower HSV was 5066 and for the upper one was 70, 106, and 189. These were selected just after trial and error pretty much, in which we were able to reliably detect the track under specific lighting conditions that we were at the moment. After that, we worked with different gains, so then we could actually implement some steering control with a PID control. This PID control allow us to calculate some error between the current heading as well as the target pose. Because in the end, since we're currently moving, it will not be always precise. So we have to like tune some of these values. So like with a high P gain, the robot will be more responsible, like more responsive, but it will cause some unstable oscillations. So then by increasing the D gain, we also were able to achieve critical damping, which was able to correct some of these oscillations. After achieving all this, we're able to develop a deep learning model to classify different signs on the road. This was done by capturing couple images and creating this data set in which we'll be extracting and capturing different images for stop signs, for turning signs, as well as for nothing. So then the robot would be able, well, the camera would be able to identify and react to the environment with a confidence at least of 0.85. So first, by separating these different images, we'll label them, go through all of it, go through different epochs, and in this case, the robot through different decision trees as well as neural networks will be able to find the best algorithm to recognize what it was showing in its case, whether it was a stop sign, whether it was a speed limit sign, or just nothing at all. In the end, the way we'll actually calculate which one was it is because with the confidence probability of like more than 0.85, you'll be able to determine whether it was one of these three. Finally, for Lab 3, we actually work more on the global planning as well as the networking. This is important because we scale our system from what this camera could see to more at a global level through networking couple cameras that were positioned above it, and then establishing an actual localization from the real time. To do this, we establish an SSH connection between our JetBot and a stationary camera bot that was mounted in the ceiling. So then the camera bot could provide a bird's eye view of the entire roadmap. Before we could do any sort of navigation, however, we had to perform some camera calibration to correct some of the lens distortion, as well as having the correct sizing for these different positions and distances. To do this, we calculated a camera matrix with focal length, which was like around like 504 to 500, a specific distortion coefficient to ensure that there was a pixel to centimeter measured and that these were actually being converted to have as much accuracy as possible. Once we achieve this, we use April tags to localize our specific JetBots. This allowed to have an overhead camera that was not just able to see everything, but also to identify our specific coordinates in a map that was able to actually keep track of a robot in real time. Let's say a robot for like a specific case was 200 and something, and all these different parts. This localization data was then put into a probabilistic roadmap algorithm, so then it will be able to find the shortest path to a specific goal. This goal would be using these different algorithms to find how many nodes and how many different waypoints it'll have. So then the JetBot would be able to go from point A to B in not just like any distance, but the shortest path for the target location.
The goal of this project is to program the robot to autonomously travel from location 1 to location 2 using the shortest distance while following roads and traffic signs. To accomplish this, our team focused on integrating the learning objectives from the lab into a single cohesive system. We started by creating a flowchart to plan the overall logic of the system before implementing any code. This flowchart allowed us to clearly visualize how each subprogram interacts and ensured that the final design was both logical and achievable within the project constraints. At a high level, the flowchart represents a closed-loop control system. The program begins by taking a map image, a pixel-to-real scale conversion, and the robot's current pose and goal location as inputs. These inputs are processed by the path planning subprogram, which determines the shortest route and outputs a navigation decision such as turning left, right, or going straight. This directly supports the objective of minimizing travel distance. After path planning, The system checks whether the robot has reached the goal. If the goal is reached, the program ends. If not, the robot continues operating in a continuous loop. While the robot is moving, camera images are continuously captured and passed to the sign recognition subprogram, which uses a trained model to detect traffic signs, such as stop signs, turn signs, and speed limits. This ensures the robot follows traffic rules while navigating the environment. The outputs from path planning and sign recognition are then combined and sent to the kinematics subprogram. Kinematics convert the high-level navigation decisions into motor commands based on differential drive motion. These motor commands move the robot, and the robot's updated position and sensor data are fed back into the system, closing the loop and allowing continuous correction until the destination is reached. We chose this structure because it is modular and easy to manage. Each learning objective is represented as a subprogram with clearly defined inputs and outputs, making the system easier to understand, test, and modify. This also reflects how the lab modules were structured, which made integration more straightforward. In terms of potential improvements, the design could be extended by improving the accuracy of sign recognition through additional training data, and refining path planning to better handle dynamic situations, or further tuning the kinematics and control parameters for smoother motion. These improvements build directly on what we learned in the labs and could be implemented incrementally. Overall, this flowchart demonstrates a practical and achievable approach to autonomous navigation by successfully integrating multiple learning objectives into a single closed-loop system.
After creating the flowchart, our group was tasked with using the ideas from the flowchart to combine skills we learned in labs 1 through 3 to make the robot do these certain functions at the same time. The functions that our group chose to incorporate together were basic robot, control and kinematics from lab 1, and sign recognition using deep learning techniques from lab 2. The way that we laid this out was that we wanted to use kinematics for the robot to move forward, use sign recognition for the robot to then turn left, and then after making that turn, use kinematics for it to go forward again, and then for the robot to see a stop sign at an intersection to then stop and complete our action of combining the skills. Some challenges that we faced were that originally we were trying to use line following with these two other functions. We had a difficult time combining the line following with the sign recognition, as the robot needed to take pictures of the lines and the signs at the same time, which was causing a delay in the camera. All in all, we were able to complete this task as shown in the video that is going to be played next. In conclusion, we were able to successfully program our robot to travel from location A to B using road following and following traffic signs. Thank you.